Okay, good. This time we'll get it right. Konstantin Meyl is Vice President of the German Association for Space Energy, who another one of our speakers is coming from on Saturday. He's from Furtwangen, Germany. That's in the Black Forest. It's the center of the clock industry. You remember those old cuckoo clocks that used to be all over the place? That's where they made them. The old clock school is now the University of Applied Sciences, and Dr. Meyl is professor of power energy and energy technology. He's been there for the past 18 years. He started at the Technical University of Munich. He has a PhD from the University of Stuttgart. He's done three-dimensional calculation of eddy currents as his thesis, and things have gone from there. He has an excellent book out there out front on scalar waves. That's one of the most difficult of all terms to define in our field, and it looks like Dr. Meyl has a handle on that. So let's please welcome him. Thank you, Mike.
The first slide, please. Yeah, welcome. I speak about the neutrino power and the existence of scalar waves. So this will be the first question. I want to find an answer whether scalar waves do exist. Is it working?
The other, you're at the...
This one?
Yeah, you have to click forward. You're at the back already.
This is forward. I see. Do scalar waves exist? Then I speak about Nikola Tesla, the father of free energy, as he is called. And I bring an example for free energy use. That will be the expanding Earth. That is a very important thing that was discussed on a conference of the Technical University of Berlin, where I've been invited. And then I speak about the current situation of neutrino research. Neutrino is an oscillating particle. Neutrino loses just as electrolysis. The splitting of water, that's another possibility to find a way to split water. And about the problems of interaction, you know the interaction of neutrinos is very weak, so we have this as a problem. And particle examples for neutrino absorption I will give to you, so practical examples. I think this is what you are interested in, and I will show you an experiment that is a historical rebuild of Nikola Tesla device. We have a problem in theory, as you have to know that the wave equation is describing electromagnetic waves, but not scalar waves. Well, we see that we have two equations. One is describing, the one is of Laplace, I'll show you later. This is the oldest description of waves, is describing as well one part of the wave which is transverse and one part which is longitudinal. And this part can be expressed by this word as scalar wave. Well, it's a mathematical description and of this of longitudinal waves. On the other hand, we have the Maxwell equations, which describe electromagnetic waves as well, but as a damping term, the vortex. And so we will have two solutions. If both wave equations are valid, then the first solution will be that the electromagnetic wave is zero, and the rest, no, is not zero, the rest is zero. That means you have no scalar waves, you have no vortex, you have an undamped electromagnetic wave, and this is the solution one you normally find in textbook physics. This is normally discussed. There is another solution. The second solution will be that we have electromagnetic waves as one part of the wave equation, but as well the rest that are vortices, field vortices, and these vortices form a scalar wave, and so both is not zero. The scalar wave is not zero and the vortex as well. So you have the possibility to explain scalar waves by field vortices. This is just what Kelvin said when he visited Tesla in his laboratory. He said, if these longitudinal waves exist, we have to work out vortex phenomena. And perhaps you know these vortex systems Kelvin has designed, and he wanted to explain by this way, he wanted to explain what scalar waves are, because he has seen in the laboratory of Tesla that scalar waves do exist. But in the theory, you have this problem. Well, let's have a closer look. Here you have the derivation of the scalar wave from the inhomogeneous Laplace equation, and if the speed v is the speed of light, then on the left side, gradient divergence E is minus curl E. This is the delta operator in vector analysis. And the delta operator, that's the Laplace operator, this is just the inhomogeneous Laplace equation. So this, if you separate the Laplace operator in these two parts, then you have on one side the transverse wave, here on the right side, which is penetrating with constant speed, with speed of light. And this is the velocity of propagation, you see, is constant. And this is the electromagnetic wave, or up to the inventor, it is called the Hertzian wave. And we know a lot about these waves, radio waves, microwaves, infrared radiation, light, and so on. What is it? Doesn't work. Here you have X-rays, cosmic radiation, and so on. We know this exactly. We are using this, but these waves are transverse waves. On the other hand, we have a description that is, as I have told you, normally put to 0 in textbooks. And because the divergence of E is put to 0, and this divergence of a vector is a scalar in mathematics. So this part here is founding scalars, and by this we are calling this part a scalar wave, as a scalar part, maybe a particle, occurs in the wave equation. And this part is a scalar, but the gradient of a scalar again is a vector. So the wave is has a direction. This is important, that the scalar wave has a direction and is not scalar at all. There's only a particle, maybe a vortex, a field vortex, that is scalar. So this is important to know. As this is a longitudinal wave, you know a longitudinal wave is has no constant speed. We know it by the sound wave, which is a scalar wave as well. The sound wave always is accelerating, braking, accelerating, braking. So the speed is not constant, and it can be slower than the speed of light. We have noise perhaps, or plasma wave is slower. If it is the speed of light, then we need to have particles. Photons are particles, as you know, in physics. So these particles are forming a standing wave or a scalar wave. And the neutrino as well is a particle in physics. That means the neutrino as well is propagating as a scalar wave. And I have the opinion that the speed is higher than the speed of light. Well, this is what I have to derive first. Here you see the properties of scalar waves if I compare them. Maybe in Europe, oh, yes. You see, that's the Microsoft problem. If you have a transmitter and a receiver and field lines in this way, these are longitudinal. That means they propagate from plus to minus, from minus to plus. In this direction we have the electric field pointer, in this direction we as well have the speed of the wave. Here on the right side, can you see it? It's very, not very strong, the lines. The lines of the electrical field pointer are just round. They move around the transmitter. So this is only part of the power that is receiving the receiver. So the fields are scattering, we have transmission losses and so on. But on this left side with the scalar wave, the field lines are focussing, bundling up at the receiver, and so they have no losses. This is what Tesla said, that we have no losses. Everything is collected at the receiver. It could be even more if you collect another transmitter in your environment. We have a positive use for the transverse wave. As we know, the radio, information distributed TV, if there are millions of people listening to this transmitter, I think this is a positive use. But if I want to phone only with one person in the world, only with one person, it's not necessary that millions of people listen to what I say. That means that for mobile phoning, this scalar wave would be the right one, and for energy conversion. I think this is energy, and the energy is received. So if you want to use it in this way, this would be a positive use. A negative use on the right side would be mobile phoning. Here, this is a negative use. It's the wrong wave, you see. I would say this wave is not allowed to use in this way as we are using today, because you touch all the private rooms, sleeping rooms, and so on, and I don't want to have them in my room, in my private room. They have to remain outside. And this is a real problem, a main problem. So this is the wrong wave, mobile phoning, and you don't have it as well? Or,
May I reformat the screen for a moment? Let me reformat the screen,
yes, you may.
and we'll see. Grant me a moment.
No, stop. Back again.
We'll go watch.
No, please do back again. I take a line out, only one line out of it. You have to, here, you have to, you see, only this switch off. How? That was. So, we almost have to do everything by ourselves. So we can see what the, oh, sorry. Back.
You accidentally pressed the mouse button? Okay, here, watch. Move it off just a little bit, get the mouse, then go back. Are you want to go back? Okay.
Good. Directional radio. Well, that's nearly the same as mobile phoning. And on the other hand, the negative use for scalar waves will be if the receiver is a human being and not a technical receiver. As long as you are using a technical receiver, you have no negative effectiveness, because the technical receiver gets all field lines and there is no rest. So if the human being is the receiver, then we speak about electrosmoke or even radiation weapons. As Tesla has spoken about radiation weapons, about dead rays he has spoken. So there is an effectiveness of scalar waves to biological systems. That's clear. Let's have a look at the wave. The electromagnetic wave is very famous. The properties are well known. And you see that this wave is propagating with the speed of light. It is a transverse wave. And so the field pointers are perpendicular to the direction of penetration. And the third point is very important, that the phase angle between electric and magnetic field pointer is 0. That's a special effect of electromagnetic waves, as you see here. Here, that if the one is 0, the other one is 0 as well. So they have just the same field angle. If I have a look at the books we have on school, it's a school book. It's a school book of physics I had as a boy. You see, the Grimsel, German, very famous German school book. It's explained how the fields are with a dipole. Here you have a dipole, and you see the electric fields like this, and the charge carriers are on top, and if they are moving, then we get the magnetic fields. That is 90 degrees later, and then we get the opposite charge, and so on. And this explains that next to the antenna, in the near field zone, as we call it, we have a phase angle between electric and magnetic fields of 90 degrees, as you see. You learn at school. That's not, that's well known. That's well known. Everybody knows that we have 90 degrees. But you have learned before, in the slide before, that the electromagnetic field has a phase angle of 0 degree. So the result is antennas are sending no electromagnetic waves. You have to know. This is if you think consequent. And, well, this will be a problem. We have to discuss again. I take the same school book, and look the next page, and then I find this picture. You have the dipoles. Here is the dipole, and you see the coming off of the electromagnetic field lines from the dipole, from the excited dipole. And what you see is that they are forming vortices. These are not, it's not a wave, it's a vortex, what the dipole is sending off. So what is the next vortex doing with the last one? It's pushing the old one. That means that antennas are radiating field vortices as a shock wave, as a standing wave, as a longitudinal wave. This is a longitudinal wave. You see, you know by the sound wave. The sound wave, there is one air particle pushing the next. And this gives a standing wave or a shock wave. And this is what we see here. This is the pushing of one vortex to the next. And so we come to the result that the dipole is only sending scalar waves, no transverse waves. But there is something happens between the so-called near field and the far field. And if in the far field, if I'm far away, that's not very long distance, that's the wavelength divided to 2p, that's divided to 6 about. So that's not a long way to go. And then the longitudinal part of the wave nearly is 0, so it's neglectable, and the rest is the transverse wave. And there is something changing, and I can explain, or could explain it in that way, that I say in the transition between the near field and the far field, the vortices unroll up to a wave. And then they are propagating as an electromagnetic wave. But in the near field zone, every specialist on high frequency technology knows that it is not allowed, he says, it is not possible, I would say, to measure the electromagnetic wave, as there is none. There is none. But what is there? This is the next question. If I have this approach that the field vortex breaks up to a wave, at the receiver, the opposite thing happens, that at the end of the antenna, the wave is reflected, running back, and you get a vortex again. So it's rolling up, the wave is rolling up at the receiver, at the antenna of the receiver, rolling up to a vortex. And so you have just the opposite thing. If you want to describe this as you don't need any energy to form the vortex into the wave or back the wave into a vortex, you don't need energy. Both are stable structures. Then I can use, or I shall use this picture, this model, that I bundle up, or that I roll up the electromagnetic wave to a vortex running with the speed of light, the constant speed, and around the magnetic field pointer. They are perpendicular to each other, you see, and perpendicular to both is the electric field pointer, and this has to be in this direction. So if you are moving this vortex in the direction of the electric field, then you have a longitudinal wave. This is standard. But there happens something, and I want to discuss this. Longitudinal waves run in the direction of the field pointer. With a field pointer, the vector of velocity oscillates, you see. The faster the oscillating vortex is, the smaller it gets. That has to do with the Lorentz contraction, because we have speeds nearly near to the speed of light. So the Lorentz contraction Einstein has used in his theory of relativity, this works at this point. That means the diameter reduces, the higher the speed will be. And this is what I've shown here on the right side. The diameter reduces the quicker it is, and if it's getting slower, then it's getting bigger again. So the diameter always is moving of these scalar waves, of these vortex systems. And the vortex permanently changes diameter and wavelength. And as you know, that we have the relation that the frequency is the speed of light divided to the wavelength. By this, if the wavelength is changing and the speed of light is constant, the frequency is changing as well. And the result is that the vortex acts as a frequency converter. So that is vortex physics. Yes, I think the universities have forgotten in the last century. But it is very important to know that a vortex always is a frequency converter. So the result is the measurable mixture of frequencies are called noise. Let me go back to the example. I have an antenna. Let me say it has an efficiency of about 80%. 80% means you are not able to measure 80% because you have to be in the far field. You measure in a distance. And then you calculate back to the surface of the antenna. You calculate back and say, okay, with a law of the distance, it is 80%. 80%. What about the 20%? 20% losses? Well, these 20% are the noise. That's the noise of an antenna, and this is the scalar wave part. This is important. This scalar wave part is the noise. And you know that every antenna is producing noise. This is what you are able to measure everywhere. And if you measure in the near field zone, you measure only noise, 100% noise. And of these 100%, 80% roll up from the vortex to the field, to the wave, and the rest remain vortices. And if the vortex decays, then it gives losses. And these losses are measured. So now we understand what scalar waves are. We work with scalar waves. We have them. So the only problem will be that we don't realize it. Scalar waves do exist, the near field perhaps, the noise, the dielectric losses, the microwave oven is heating the water and so on, and you always have the decay of the vortices forming scalar waves. So these is existing. I think I have found a clear answer to this question. And I can say that scalar waves still are in use. Please remember these transponder systems you have in the entrance of a drugstore. So where you have a chip card or something like this that is receiving the energy from a transmitter, and you know that the transverse wave is not transporting, has not the properties to transport energy. It has to be the scalar wave part. And this is still in use nowadays. And this RFID technology, this is very famous at the time, not only in Germany. Well, let's talk about Tesla, because he had been the first one who did not describe it in a theoretical way as I do, but he has made a lot of experiments. And he was a very famous and perfect experimental physicist. And he has found out a lot of properties of these scalar waves. As the scalar waves, you have to know that noise is a scalar wave, okay, but a scalar wave is more than only noise. So if you are using the scalar waves, you have much more properties you are able to use, and you have to work it out. You have to make your own experiments to find out what properties these very important waves have if you want to use them, perhaps for energy devices. Tesla has constructed this laboratory, you especially know, at Colorado Springs. It has had 10 kilowatt power in 1899, and he was transmitting energy over a distance of about 30 miles with more than speed of light. He has found out with an over-unity effect. He has described it as a scalar wave, a standing wave. He has found out by a small receiver. He has measured the knots and so on of the standing wave, so he could find out that it is a standing wave, it is a scalar wave. And he as well has shown the biological effectiveness. Well, this is not amazing. That's clear, because if you are measuring a human being from head to feet, what are you measuring? Noise. Yes, we are producing noise, every one of us. So we work with scalar waves. This is important. That's why there is a physical combination between the energy use of scalar waves and the medical use. There is always a combination. Not with the transverse wave. The transverse wave is only acting if you have antennas here. Well, for mobile phone, you would need to have 16 centimeters. I don't know how many inches it is. 16 centimeters. That's a lot. I cut them, so I have no problems. This is the patent of Tesla, and he measured the resonance of the Earth. I don't want to give a comment, because you need to know that if you want to find out whether these derivations of Tesla, these properties he has found out, are correct or not, you have only one way. You can't ask him, he's dead. But you have only one chance. You have to repeat the experiments. That's what you have to do. And then you find the answer. So he told us that the resonance he had found out would be 12 hertz. The Hertzian wave has the resonance, if the Hertzian wave is running around the Earth, that's a Schumann resonance of about 7.8 hertz. And this Hertzian wave is propagating with the speed of light, while the other one may be quicker if, and this we have to prove, if the wavelength is constant, then the relation between the transverse wave of the scalar wave to the transverse wave, this relation is the same relation as the speeds have. That means you get a scalar wave that propagates with 1.54 times the speed of light. And well, this is what you are able to read in his patent from 1890, I don't know, 99 or something like this. And you have to prove it. And this is what we have done. Some students in my university and we have realized a reverse engineering of the Tesla transmitter. We have used an identical schematic diagram, and we have got, and this is very interesting, the same results. First of all, we wanted to rebuild it one-to-one. That would have been a very huge Tesla coil. As you know, how many miles he has used for his coil. And so I have not found a company to pay for it. Well, I've discussed it. They've had interest in Germany, in Austria, and so on. But at the end, they said, oh, our energy equipment is not paid yet, and we have to wait 40 years, I think, till it is paid. They have no interest. Okay, and then we said, what shall we do? We have not the money. We reduce the size. If we use a higher frequency. Tesla has used about long waves, or nearly very long waves. I'm using now short waves, so the size is reduced, as you see here in the picture. And we are able to measure with this. And we find out the Tesla wave at 7.1 megahertz and the Hudson wave at 4.6 megahertz. This would found that this wave as well oscillates with 1.54 times the speed of light. Well, this is what I want to show you now. As this is the original device, I'm using, let's go back. I'm using Tesla coils. As you see, these are air transformers with the primary and the secondary coil. This is a pancake coil, as you perhaps know, and perhaps you know that these pancake coils have other properties than a cylindrical coil. We have proved this, and it is correct. And in the middle, we have this spherical electrode and connected, and the other end of the coil has to be earthed. Tesla said, well, he was using an earthing, a real earth, but I'm using only an earthing line, as he worked with about 60,000 volt tension, very high tension, and I'm working with 2 volt. That's very little, 2 volt. Well, I only want to show whether the effects exist or not. And so there are differences, but let's have a look at the properties. Here we have the frequency, and I now go up with the frequency. I hope you can see it. The lamps at the transmitter are shining, and I show you later that one diode is demonstrating the positive and the other one the negative part of the wave. And the higher the frequency will be, I find out that there is one frequency at about 4.7 it is here in Salt Lake City. Well, there the receiver receives something, but what the receiver is receiving is very easily shieldable, and this may be the Hudson wave. As the Hudson wave is shieldable, another possibility is to switch off the earthing line and to watch whether there is an effect from the receiver back to the transmitter, and you see that the transmitter doesn't mention it. So you see no effect. And this is typical for transverse waves. So I think at 4.7 megahertz we will have the resonance of the transverse wave between transmitter and the receiver. And now I change the frequency as well. Again, the lamps go out at the receiver, and suddenly they are shining very brightly, especially if the lamps at the transmitter go out. Now, if I pull the earthing line, they shine again. But if the receiver is receiving, then they go out. So the transmitter feels whether the receiver is switched on or switched off. This is a special property of the scalar wave, as I've shown you by the field lines, that now the field lines have another properties. They are running from one spherical ball to the other electrode. And yes, and it is not easily shieldable as well, so this may be the scalar wave. And I have, we have produced a lot of Tesla coils, and we are using now these ones. In the experimental set we have different sizes. This one is a very, it's one with twice of the wavelength compared with this one. And so you can make experiments with it. We have designed them that you are able to compare the properties, that you are able to show the transverse wave and the scalar wave with the same device, so you are able to compare both. And because it's very easy to produce only one part and not the other one. But if you want to find out what the speed, perhaps the speed of propagating is, then you need to know the frequencies. Now we have 7.4. If somebody is able to calculate this, please do this. 7.4 divided to, what was the other frequency? It was this one, to 4.7. Is there anybody who is able to calculate this? How quick is the wave at Salt Lake City? Well, calculate it and tell it later. Maybe about 1.4, 1.5 times the speed of light. Okay.
1.57.
How much is it?
1.57.
1.57. Thank you very much. It's quite quick. It is. So you see, it differs, and it has nothing to do with harmonics, because harmonics always have twice or four times more than the resonance is. This is really changing up to the distance, to the sphere, to the conductivity of the air, to the air pressure, and so on. So this is typical for longitudinal waves, as you know, that the sound wave as well is changing in water, in matter, and in the air. You have different results. Okay. Here you see the spherical diagram. If you have a resonant circuit, this is well known what a resonant circuit is in physics, with a capacitor and an inductance. And if you separate both in two parts, you're using two air transformers, you are separating the electrodes and the distance between them. That means you get an open system. Now you get an open system. At the end, you have the Tesla system with the transmitter and with the receiver on the other side with the earthing line. Tesla was really using the earth. I'm using the earthing line because I don't want anything else to go into resonance. Otherwise, I wouldn't receive anything at the receiver because of the very low tension. And you see that this open system first acts very, very usual, as you have learned at school. But there are some effects that are occurring in addition. And these effects are the most important thing. And what we have found out is that this wave is, this field of a capacitor, if you are opening the capacitor, are propagating as a wave. And this is new. And this is what normally nobody knows, that this is a wave. It is a longitudinal wave, that the fields are longitudinal in a capacitor from one sphere to the other. That's standard. But that it is a wave, propagating as a wave, this is new. And that you are able to measure the knots and so on. This is new. And that this is quicker than speed of light is new as well, as if you measure the knots, the distance from knot to knot, you have the wavelength. There's no doubt about. You have the frequency counter. You know the frequency. That's no doubt about. So you are able to calculate the speed of propagation. Do it. And this was my opinion, that everybody shall do it. And so I'm selling this case and this experiment, that it will be done as often as possible and reproduced, because this is very important for science. The field lines of the capacitor go from electrode to other. Long-term new is that they show the properties of a wave, of a scalar wave. This is new. The science value is the importance of the experiment for the science community exists there in that first. We get an answer whether Tesla was mistaken. There are a lot of people who say Tesla was mistaken, but they have not proved whether this is true. So this is what you have to do first. You have to prove it, and then you can say he was right or wrong. And I think he was not mistaken. That was correct, what he said. This is the first effect. The next is that the properties of scalar waves can be studied. Where do you learn it? Never. Nowhere. Nobody is explaining to you. I do. Okay, but no teacher, I think, elsewhere is explaining what properties these scalar waves have. And they have very interesting properties. And you have to find it out. The best is you do it by yourself. Then I think you agree with it. The reproductivity, oh God. Finally is given. Okay, thank you. You can read it. The near field can be explained as the field of scalar waves. Yes, I've explained to you. And the noise just as well. Okay, let's read in the New York Times. Nikola Tesla has written, until 1898, I obtained mathematical and experimental proofs that the sun and other heavenly bodies, similarly conditional, emit rays of great energy, which consists of, you can read it much better than I see it only this way, inconceivably small particles animated by velocities faster, excepting that of light. So he have found out that these particles, very small particles, are quicker than the speed of light. And he said, so great, the penetrative power of these rays is that they can traverse thousands of miles of solid matter with but a slight diminution of velocity. And you see, there's no particle in physics that has these properties without the neutrino. So I have the opinion that Tesla, as he is called the father of free energy, is the discovery of neutrino rays, because he has been much earlier than Pauli. Right. Yes. And he has shown the properties and he has used the neutrinos. We are not able to use till right now, you see. That's very important. So the effects are that it is a transportation of energy with more than speed of light is reality in physics, and this is a problem because only the group of a wave is transporting energy, not the phase. It has to be the group, and this, I think, is a problem. As with this experiment, you can show that you are able to transport energy with scalar waves quicker than speed of light. Experiments which show velocities quicker than speed of light are very famous, but the colleagues, they always say, oh, that's only the phase, speed of the phase. But here we have energy. And we get a conflict with the postulate of the relativity theory of Einstein. I want to give you an example, as I've talked about at a conference of the Technical University of Berlin about the expanding Earth, and I had shown that this is a converter. The Earth is a converter of free energy, because if the Earth expands, and if this happens, that we need a reason. Well, we have hints for the Earth expansion, and this can be found in the spheres of geography. If you have a look at the mountain formations, that's not my space, but there had been some other colleagues speaking about this to show it. Geology, yes, that is plate tectonics. Plate tectonics is the theory they are using. There we had colleagues as well, and my part was the physics. This is fundamental research. I want to explain to you what the physical aspect of this is. And there is a book of Hilgenberg from 1933, Vom wachsenden Erdball, of the expanding Earth, I would say it is in translation. And he has shown that if the radius, if the diameter of the Earth changes, you get problems. You get you get forces here and here and at this point again. The result will be that the crust will break in the middle, or here, or you get these effects that parts of the crust dropping down and so on, getting valleys and so on. So we have some effects that can happen and can have to do with the expanding Earth. And if we have a look of the ocean, of the Atlantic Ocean, then you see here that it is a formation that seems to be like, that there is something drawing the Earth into pieces. We are able to measure it. It is about 10 centimeters in 1 year, in average. Because the shelf line fits exactly in the shelf line of Europe and Africa, here of America. They fit together. This is what Wegener has said, Alfred Wegener, the Continental Drift. The shelf lines of the continental plates of America and Africa, they fit together, and the seabed of the Atlantic, as you see here, the seabed shows just these properties. If the diameter of the Earth remains constant on the other side, that means on the Pacific Ocean, the seabed must have a very different picture, must give a different picture. But it's very interesting that it does not. You see the same formation. Running up here to California, in a few thousand years or so, it will be an island. And if you measure the whole ball of the Earth, you can only measure it from the space, but the NASA has done it, and I have a paper that shows that they measured that the diameter of the Earth is growing. And it is possible to measure, because you can't measure it because of the Pacific is too big. You can only measure it on the Atlantic, but not on the Pacific. If it's more than half of the Earth, then it's impossible to measure whether the Earth is expanding or not. So we see some effects, and now we are able to calculate this. First of all, the reduction of the Earth's rotation will be a hint, because the bigger the Earth will be, the slower it will rotate. That's a physical law. That's and you are able to read in Bild der Wissenschaft in Germany. I don't know what it is in America. Thank you. The day on the ascent Earth has had 5 hours. 900 million years ago, one day has had 18 hours. In Science, it was an article. Then every year is escalating of 0.73 seconds in 1 year. You know this this second that they fit in from year to year to coordinate it, because these atomic clocks are so precise, so that we can find it out very exact. And well, there's another hint that 2,300 years ago, Aristarchus, a very Greek scientist, has given the days of a year very exactly, you see. It's astonishing how exact the date is well, this is. And nowadays we have this, that means 365 days and a quarter of a day. And the difference are 500 seconds, and in the average over the 2,300 years is 0.22 seconds per year. That means if these values are correct, then the average of the expanding Earth was less in the last 2,300 years than it is nowadays. The Earth is expanding actually quicker. This is measured in Germany. This value is measured by the government, Physikalisch-Technische Bundesanstalt in Braunschweig. They have the exactest clock, and this is the clock where our clocks are driven. And so you are able to calculate. I have to do it a bit quicker because you're behind me, yeah? Okay, I try to do it. The annual change, you are able to calculate because there is a relation between the time that the Earth is turning slower and the change in diameter, and you are able to calculate this, and this means the average over the last 2,300 years was 5.5 centimeter, and nowadays it's expanding about 19 centimeter. And this is just what the NASA measured. So this effect is exactly the same as what they measure in the time, then they measured in diameter. And I think this is interesting. Okay, this I think we don't need. Well, then we would have to speak about the properties of neutrinos. I think that's too much. Yes, I can't do this because
You can have 7 more minutes or 8 more minutes. How's that?
yes,
Will that do?
well.
Will that help?
The problem is, I explained some points. The problem is that the neutrino oscillates between the properties of an electron and of a positron, and the average of the charge is 0 and the mass as well. So this is what we are measuring. But the effective value is not 0. And you know, just like AC current, the average of the voltage of the current is 0, but the effective value is not 0. So it's up to what you are measuring. And the result is that you have a particle with no charge, with no mass, but it has energy and it has impulse. And this is the only possibility to explain why these particles exist. And we call them neutrino. And our solution will be that this energy is free energy. We are able to use it at any time and everywhere as an available energy resource. And this, I think, is an interest to us as we are looking for energy. So the neutrino is a physical particle. And that's why I'm working with this model of neutrinos. And I don't work with 0-point energy because 0, there's nothing. I don't work with, what is it, vacuum field energy or something, vacuum, there's nothing. So you see, the neutrino exists. They have given the Nobel Prize to the neutrino research in 2002, and so this is existing, and you have a particle that exists and that has energy, is carrying energy. You only have to find out how to interact with this particle. Well, let's have a quick look. You know that they measured a rest of the mass, but this causes that the speed has to be slower than the speed of light. Well, but the neutrinos are coming from a black hole, and a black hole is black because there is no light coming out. So the neutrino has to be much quicker than speed of light if it wants to come out from a black hole. And this is what Tesla said. And well, I think the water in these big detectors, this water breaks the radiation, and I explained it in that way. If the water molecules are oscillating in resonance with the neutrino, they give energy to the neutrino, they are break by this, and the neutrino will become an electron or a positron. If it is a positron, an anti-matter, then you see lightning. This is what they are measuring. If they measure only some lights a day, these Cherenkov radiation, and if this is only one part they're measuring nowadays, and the other, the electron, founds neutrinolysis, that is splitting water, you see. So this is what we can use. Perhaps you know Stanley Meyer. This would be one application to split water by neutrino radiation. I have this as an example. Well, it has to do with these open field lines outside an electron. This is the model of the electron, and you have to realize this in a technical device. And so Stanley Meyer has used just the same charge. Okay. Then we had another problem. The third problem was that the quantities were different. We had only 3 billion measured in the Kamiokande, but 66 billion neutrinos measured in the Galax detector of the European detector. And the question is why this? The colleagues of science had been very astonished that they measure only such small parts. They have not expected. And was it a fault in measurement or in the model? Well, my solution would be that by the Kamiokande, we are measuring the light. The light means we measure that part that is materializing of the neutrinos that are materializing into antimatter. That is only the smaller part. And in presence of matter, we get much more electrons, and they are splitting water, but this is not measured nowadays. This had been measured by the Galax detector, and so we have this relation that is as well the relation we are measuring at the sun. If you calculate what the sun is producing light, or the sun is producing matter and is growing. So we have the same effects. Well, the question is, science are discussing whether the first hypothesis, are the neutrinos changing but not measurable, or are they absorbed? If they are absorbed in the center of the Earth, then the sun supplies the Earth with neutrino power. This is the consequence. And this is very easily to understand. But on the other hand, this one is not easy to understand, but this is honored by Nobel Prize. Well, this is the back of the medal. You see, in both cases, we have the problem that the interaction with the center of the Earth, with the core, is much bigger than the theory allows it to be. Much bigger, 10,000 times bigger. So we have a problem with the interaction because the weak interaction, it cannot be. And this is what I describe here on this slide, that if we have only the static interaction, we have gravitation, or we have electromagnetic interaction. If it is oscillating, then the average is zero, though we speak about levitation. And if the electromagnetic interaction is as well changing in time, then I speak about the resonant interaction. And the weak interaction is only a special case of this. And this resonant interaction, this is working if neutrinos are interacting with the core with the center of the Earth. I think now I have to stop it, or I get enemies. Thank you very much.